Alright, today we will talk about Hierarchical Reinforcement Learning or HRL. So, uh, let's start with what this is all about. HRL, for short, is basically a way to manage complex tasks by breaking them down into smaller, more manageable pieces. And instead of trying to solve everything at once using one big flat policy, we organize the agent's behavior into layers. Each layer takes care of a different level of decision making. Now, why do we even bother with this? Well, think of that. Traditional reinforced learning can struggle in complicated environments, especially when rewards are sparse or the tasks are really long. You don't want your agent randomly stumbling into the goal after thousands of steps. So the idea is you break the problem up. You use a higher level policy to set intermediate goals and then you let the lower levels figure out the details. You can think of it like giving directions to someone. At the top level, you say go to the kitchen. That's your high level instruction. The mid level might say walk forward and turn right. And the low level is handling the fine-grained motor control, each individual step and movement. Okay, and there is a quote here that sums it up pretty well. It says that hierarchical is essential for intelligence because it lets us simplify problems, break them down, and reuse skills instead of starting from scratch every time. That's kind of the key benefit here. We are not reinventing the hell on every decision. Okay, close down. Okay, now let's look at the architecture itself. Right now, we have set the number of hierarchical levels to 2, and let's make it 3 or 4, and let's make it 3. You can adjust that from 2 up to 4 depending on how much abstraction you want. And over here, we have got a slider for abstraction. You can see here. Okay. That just means how far apart the levels operate in terms of time steps. Higher abstraction means the upper layers act less frequently, setting longer term goals. So here's what each level is doing. At the top we have the high level policy, and this one's in charge of decomposing the overall task. Its job is to choose a sub-goal which it samples from policy highs. Okay, I mean here. That means given the current state S, it selects a sub-goal G. In the middle, we have the mid-level policy, that's pi mid and A sub mid SG. So it takes both the current state and the sub-goal and outputs a mid-level action. You can think of this as breaking the sub-goal into smaller parts. And here the low-level policy, which is the one directly interacting with the environment. It works with pi low A and SG. So again, it sees the current state and the sub-goal and chooses a primitive action A. This is where the real-time control happens. And here you will notice it's currently updating, and we can see the number of level actions taken so far in this case. And here, for example, 720. Okay, so the agent is actively working toward the sub-goal, which in this case hasn't been updated yet. It still shows none. Okay, now we have the sub-goal space. These are the possible sub-goals that the high-level policy can select from. In this example, we have got 4: explore room A, here, find key, open door, and reach goal. Right now it's showing the first one, and these sub-goals are predefined and give structure to the agent's exploration. Right below that we have got the instant reward mechanism. This part is important for training to low-level policy, and instead of just relying on the external reward from the environment, we also reward the agent internally when it achieves the sub-goal. So if the agent reaches a state where the sub-goal is satisfied, it gets a reward of +1. Otherwise, it gets 0. And that's what this formula means here. uh, R sub I Sg equal success Sg, and here +1 or 0. And this helps the agent learn even when the main task's reward is delayed or sparse. Now let's look at the environment block. This is a simple grid style world, and we are visualizing a hierarchical task happening here. And this blue dot represents the agent, and the red dot is the final goal. As you can see, the agent moves step by step, and here the steps, and it's trying to achieve its current sub goal before it eventually reaches the red dot. And finally, we have got the experience buffers down here. These are where we store the agent experiences for replay, and they are split by level. The high-level buffer contains transitions in the form of SG, which means state and sub-goal. The low-level buffer stores SA and state and action, since it operates closer to the actual environment. And these buffers are used during training. The agent samples from these to update its policies, and at each level, high-level updates happen less often and are based on external rewards, and low-level updates are more frequent and use interesting rewards. And that's okay. Okay, let's pause here for a second and go over what really makes hierarchical reinforced learning work. We had touched on the big idea earlier, breaking down a task, but let's be more precise. There are a few things that make HRL useful. First, temporal abstraction. What's that? That just means we break the task down by the time scale. Some decisions are made frequently, some less often. Then we have policy structure. In a regular RL setup, there is just one policy deciding everything. Here we have separate policies at different levels, one for high-level planning and others for lower-level execution. Next is subgoal generation. This is how the higher levels communicate. One layer picks a subgoal and passes it down. The lower level's job is to reach it. Fourth is intrinsic motivation. This is a reward that the agent gives itself based on whether it hits the subgoal, not based on the environment. That's important when external rewards are too sparse to learn from. And finally, here sticky reuse, and if a level policy learns how to do something useful, like open a door, that same policy can be reused across different higher level tasks. And let's look at something called options framework. This is one of the standard ways to implement hierarchy in reinforced learning. It's basically a formalism for how to group actions together over time. So instead of just picking a single action at every time step, an agent picks an option, which is like a mini policy that runs for multiple steps. Each option is made up of three things: an initiation set, a policy, and a termination condition. And the formulation is here O equal and I pi beta. The initiation set I TASAS, where option is allowed to start in which states, and the policy pi defines what the agent should do while the option is running, and beta is a termination condition. It's a function that says how likely the option is to stop at each step. And what's the point all of that? What are the actual benefits? We will look at this. First, temporal abstraction. Just like before, the agent's not acting at the same granularity all the time. Options let it plan in bigger chunks. Transfer learning, if you have trained an option that solves a certain subproblem, you can reuse that in a new task without starting over. Third, it improves exploration. If you only act at the level of individual steps, it can take forever to stumble into useful behavior. But if you can pick structure options like go to the other room, the agent can get around more efficiently. And finally, using options turns a standard MDP into semi-macro decision process. That basically just means the actions now last for variable lengths of time, not just one time step. And now we move on to the feudal networks. This is another way to bring hierarchy into reinforced learning, but it's structured more like a manager-worker setup. And here the high-level components acts like a manager. It sets a goal for the lower-level worker. That's the only thing the worker sees, not the global objective, just a sample passed down. The worker then acts to achieve that goal, and if it succeeds, it gets a reward. This setup leads to what's called goal-directed behavior. Instead of waiting for feedback from the environment, the worker is rewarded based on whether it satisfies the manager's instruction. And now there are some extra things going on under the hood. What are the feudal networks? Use something called a dilated RNN. This just means the higher level policy runs at a slower frequency than the lower one, which fits the whole idea of abstraction over time. And goal embedding, instead of communicating goals as plain coordinates or actions, the manager sends down a goal vector, and embedding, which gives the worker a bit more flexibility in how it chooses to interpret that goal. And okay, advantages here. So one issue in standard reinforcement learning is credit assignment, figuring out which actions led to a good result. When you are dealing with long time horizons, that becomes a mess. With HRL, because each level has its own role and its own rewards, you can split that up. That's what we mean by multi-skill credit assignment. Then there's abstract goal representation. Instead of telling the worker exactly what to do, the higher level policy can just communicate a goal in a more general format. The worker then has the flexibility to decide how to handle that. Another thing is transition independent optimization. So here the different levels can be trained somewhat independently. They don't have to wait for each other at every step. That helps with stability. And the last one in here is about exploration. By giving to lower levels the directional goals in this abstract space, you end up guiding the agent more efficiently instead of just letting it wander around hoping to get lucky. And following is here, training process and other things. And here pseudocode. We set up the networks at the very beginning. So we initialize the high level policy, its value function, and then do the same for the low level ones. We also set up two buffers, one for each level where transitions will be stored. Then the main loop starts. For each episode. We reset the environment and run the agent until it hits a terminal condition. So first the high-level policy decides if it is time to set a new subgoal. If yes, it samples a subgoal based on the current state and stores that transition in the high-level buffer. Then the low-level policy takes over. Given the state and subcode, it picks an action. The environment gives back the next state, a reward, and a down flag. But here's the twist. In addition to the usual reward, we compute an intrinsic reward. This is based on whether the agent managed to hit the subcode. If it did, the intrinsic reward is 1, otherwise it is 0. And what can I say? That's okay. And that transition, including the state, subcall, action, intrinsic reward, and next state is stored in the low-level buffer. The external reward from the environment is passed back to the high-level policy and accumulated. Then we update the state and move on. And I'm looking. One more thing, update frequency. Low-level policies usually update more often than high-level ones. So if it is time, we sample a batch from the low-level buffer and do a gradient update using whatever RL method we are using. Same thing applies for the high-level, but less often. And we have got update rules for both policies and here high-level one. This is updated based on the gradient of the log probability of the chosen sub-goal, weighted by the high-level value estimate. The idea is that we are reinforcing sub-goals that tend to lead to better long-term returns. And low-level policy update, it looks similar, but this one's based on the state and sub-goal pair, and the gradient is scaled by the low-level value function. And remember, this level uses the intrinsic reward signal. Okay, and okay, here approaches. So you will probably come across a few well-known architectures here, and they each handle the hierarchy in their own way. Feudal networks or just fun in this one, or fun here. And in this one, you have got this idea of a manager and worker. So the manager is not doing the actions directly. Instead, it's setting abstract goals, and the worker is the one actually figuring out how to carry them out. They also use this deleted RNS, which just means the different parts of the network can operate at different time steps. So they are not all updating at the same phase. And options framework. This one's been around for a while. What it does is it takes the standard RL setup and stretches it to include temporally extended actions. So instead of just choosing a simple action at each time step, it can select these higher level behaviors that unfold over time. Each option comes with three parts: when it can be started, how it behaves while it is active, and when it should end. And Hero, short for Hierarchical Reinforced Learning with Off-Policy Correction. This one focuses on sample efficiency, which is always a concern in RL. It basically uses hindsight to reinterpret the goal and make learning faster, especially when the sub-goal wasn't achieved as expected. And Hack, Hierarchical Actor Critic, it learns multiple levels of policies at the same time, and instead of just trying random actions, it uses this structured exploration method along with insight transitions to learn more effectively across levels. MaxQ, what is that? This is more of a value function perspective. So it breaks a problem down into subtasks and assigns a value to each. The total value of solving the full task is basically the sum of the values of the smaller ones. And HRL with insight is a kind of like combining ideas from earlier. It allows the agent to learn from failed attempts by attempts by pretending that whatever outcome it ended up with was actually the intended goal. It turns out that this kind of reframing really helps improve learning speed. And okay, now what are some of the main attempts going hierarchical in the first place? And one big reason is long horizon tasks. With traditional RL, you know, the learn process struggles. But if you split the task up, it becomes much easier to handle and learn. And transfer learning. So if you are already learned a skill in one scenario, you can carry that over into new task without starting from zero again. And structured exploration is a big deal here. When the environment has very sparse feedback, it helps to guide the agent more intelligently instead of just wandering around randomly. There is also the idea of compositional learning. What is that? That means you can build up new behaviors by combining previously learned skills, which saves a lot of time and effort. Temporal abstraction is also a core benefit. Instead of thinking about every tiny step, the agent can focus on high-level decision points. And robustness. Since the low policies are specialized and the high-level policy just sets general goals, the system as a whole can adapt more easily to small changes or unexpected dynamics. Okay, so all of these benefits really point to why hierarchical reinforced learning has gotten so much attention. But where is it used? Robotics is a big one. Think of a robot assembling parts. It doesn't need to learn the full task from scratch every time. Instead, it can learn motion primitives and combine them to handle more complex actions. Then there is gaming. In strategy games like StarCraft or Dota 2, the agents have to handle multiple layers of decisions, everything from controlling individual units to making big picture plans. A flat policy wouldn't be able to do that well. And in self-driving cars, this setup is useful too. You have got route planning at the top, then decisions like overtaking or stopping, and finally low-level motor control. It makes more sense to separate these out instead of training a single policy to do everything. And we also see it in resource management. Systems like data centers, energy grids, or even traffic control can benefit from hierarchical setups since the decisions happen across different timescales and layers. So, all in all, hierarchical RL gives us a framework that's better aligned with how complex tasks are structured in the real world. It doesn't try to solve everything in one go, it breaks things up, delegates, and reuses what it's already learned. And that's all for this lesson, and thank you for listening.